science since 2011, and he has been working in the field of IR and NIR spectroscopies and in the related chemometrics. And today he will talk about variation of near-infrared spectrum of water upon dissolution of various solids. Please, Professor.
Thank you, Chair. Also, this session is application session, but my talk is very basic. We apply near-infrared spectroscopy and chemometrics to examine the hydrogen-bonded network of liquid water. Here, I'd like to show some results of our analysis. Originally, I don't want to start the experiment of aqueous solutions because the behavior of aqueous solutions is very, very complicated. But some of my students very strongly want to start this experiment. So I thank these students. And Dr. Yoshimura is helping us to on the chemometric calculations. So, as in the hydrogen-bonded network in liquid water changes by dissolving other substances. The changes are highly dependent on the solute. Near-infrared spectroscopy is one of the best techniques for the change directly by observing overtone band due to the Awaji stretching, whose shape affects sensitively the change of the hydrogen-bonded network. For example, many of you are very familiar with this picture. The temperature dependence of the overtone band of Awaji stretching in near-infrared spectrum. As the temperature rises, the spectral component in the lower region decreases, while the component in the higher wave number increases. So, hydrogen bonded is dissociated to weakly hydrogen bonded to make a weakly hydrogen bonded or a non-hydrogen bonded water. So change of the hydrogen bonded network of water is clearly observed here. Since spectral changes are much more complicated for solutions, we have applied chemometrics to decompose observed overtone bands into components to know how many components exist in the variations and how the hydrogen bonded network of water is affected by solute. It is important to find any realities in the complicated changes or to elucidate common components constituting the changes. We have investigated 4 types of solutes: inorganic salts, aprotic polar organic compounds, polyhydric alcohols with an alkyl chain, and alkyl polyamine. Today, I will report the first 2 groups of compounds. The findings relating to the 4th compound will be presented at poster number 1 tomorrow. Firstly, organic salts as solutes. We measured near-infrared spectra of aqueous solutions of 42 salts, shown here: 16 sodium salts, 5 magnesium salts, 11 ammonium salts, 9 chloride salts, and 7 sulfates. There is some duplicate counting, 42 salts in all. Details of the experiment are summarized here. Concentration was set at from 0.1% to 0.5% in molar fraction. Temperature is stabilized at 20, 25, or 30 degrees. As a representative measurements, I will show you the results obtained for aqueous solutions of sodium salts. These are the spectra of pure water and aqueous solutions of sodium carbonate and sodium perchlorate at 5 different concentrations. The The variations of the spectrum are so small because of the concentrations of solutions were very low. It is difficult to recognize the variation, so different spectra representing spectral variations were calculated. In the right-hand side, the different spectra obtained by subtracting the spectrum of pure water are shown. By dissolving sodium carbonate, the spectral component in the lower region increases, while the absorption in the higher region decreases, showing that the hydrogen bond network strengthens by dissolving sodium carbonate. On the other hand, dissolving sodium perchlorate, this one, the component in the lower wave number region decreases, while the component in the higher frequency region increases, showing that the hydrogen bonding network weakens. It should be noted that the variation for sodium carbonates and for sodium perchlorates are in opposite directions, but they are not symmetric. Aesthetic points and peaks indicating the maximal changes are observed at different wave numbers for the solutions. Then, we would like to know whether these are essentially different changes or not. We'd also like to know how many components constituting the variations are. Spectral variations observed upon dissolution of other sodium salts are summarized as different spectra here. The variation depends on the solute map. Spectra surrounded by red shows the weakening of hydrogen bonding upon the dissolution of the solute, while spectra surrounded by blue shows strengthening of hydrogen bonding. In order to analyze these complicated spectral variations systematically, principal component analysis PCA was performed on all spectra of 80 aqueous solutions of sodium salts and pure water measured at 3 different temperatures. Results of PCA shown here. Loadings for first 3 principal components are shown. As the PCA as performed on the observed low spectra without being mean-centered, the first component corresponds to the average spectrum. The second and the third components explain the spectral variations. Contribution ratio shows that more than 99.8% of observed spectra could be reproduced by these 3 components. Contribution ratios calculated excluding the first component revealed that more than 99.9% of the observed spectral variations could be reproduced by component 2 and 3. Complicated spectral variation are found to be composed of only 2 components. Really, it is an important finding. And there is another very important finding. PC2, that is green line, loading for PC2 is almost the same as the component observed for pure water on the temperature variations. So the variations are composed of the change upon the same change as the temperature variation and another changes. This is a score plot for aqueous solutions of sodium salts. The score on the third component against the score on the second component of each spectrum measured at 20 degrees are plotted. The plot for pure water is here, this this one, or this. Here, and here, and sorry. For each salt, the plot was found to yield an almost linear variation. From the plot for pure water in a specific direction. Linear variation means that the spectral variation contains constant ratios of the second and third component, regardless of the concentration. For sodium salts, there is another interesting point. The salts weakening hydrogen bonding and those strengthening hydrogen bonding affect water in quite different ways. The salts weakening hydrogen bonding, this group, affects the hydrogen bonded network as the temperature rises. So plot move to left horizontally. On the other hand, the salts strengthening hydrogen bond affect will form strong hydrogen bonding, which is not formed by temperature change. Therefore, the plots move vertically. The mechanism of this difference has not been clearly stated. Similar results were obtained for the salts in other groups. Results of PCA performed on spectra of 42 salts are shown here. Approximately the same loading as for the sodium salts were obtained, even if spectra of 42 salts were included in PCA. About 99% of the observed spectral variations could be reproduced by the second and the third loadings. Score plot for 42 salts at 20 degrees, shown here, shows an almost linear variation starting from the plot for pure, around here, plot for pure water in a specific direction. Now, let's summarize the results. Most of the spectral variation for the aqueous solutions of salt can be explained only by two components. It is surprising that the complicated variation of spectra can be explained only by two components. The first component, which corresponds to the second loading, is a component similar to the spectral variation observed by temperature change of pure water. The third component affects absorption at low wave number. Low wave number is around here, which is due to strongly hydrogen bonded water. There is a peak at higher wave number for second component. This one, this one. The origin of the peak has not been elucidated yet, although we are considering the possibility that it might be due to hydroxy ion or uranium ion. We are considering also that the examination of the components higher than PC3 may be needed, but abundance of higher component is very small, and we can only get very noisy loading. So we have to measure spectrum much more precisely to analyze components higher than PC3. Results found for the score plots. The plot varies linearly with concentration for any source. Linear variation means that the ratio of the contribution of two components is constant regardless of concentration of each salt. This is the reason why isospecific points are observed at different wave numbers depending on salt. Okay. The results obtained through the analysis suggest that equivalence shown here for the aqueous solutions of salts. Non-hydrogen bonded or weakly hydrogen bonded water is in equilibrium with the two kinds hydrogen bonded water. One is hydrogen bonded water, same as that produced by temperature change, while the other is strongly hydrogen bonded water that cannot be produced by temperature change. Abundance ratio of the two kinds hydrogen bonded water is constant for each solute within the concentration range employed here. It's a very low concentration here. Next, I have no time, but next the results for organic compounds are shown. 8 kinds of compounds were examined: dimethyl oxide, acetone, THF, acetonitrile, and so on. Aprotic compounds were selected so that the hydrogen bond between solute and water does not make the story very complicated. Details of the experiment were shown here. In this case, the concentration is rather high, from 2.0% to 10%. Here again, representative observations are shown. There is a spectra of pure water and aqueous solutions of dimethol and acetonitrile. As the concentration increases, the absorption decreases because of the decrease of concentration of water. Careful examination reveals that the spectra of the solution at 10%, this one and this one, is differ little. In order to see the difference clearly, different spectra are calculated after the spectra of solutions were approximately normalized to that of pure water at the peak wave number. By mixing dimethyl oxide, absorption in the higher wave number decreases, and that in the lower wave number increases. So then this one. It's showing the strengthening of the hydrogen bonding network. Further to nitrogen, the result is rather complicated. Absorption in the higher wave number decreases, and that in the lower wave number increases. But here, around here, 6,400 wave number, absorption is increasing. Although the hydrogen bonding network weakens, some water seem to form very strong hydrogen bonding. Spectral variation for other compounds are shown here. Although the variation depends on the solute, it should be noted that absorption around 7,100 wave number around here weakens upon mixing the organic compounds, showing that the hydrogen bond network strengthens. In addition, absorption intensity around 6,400 wave number increases for all compounds. Mixing polar organic compounds causes the formation of strongly hydrogen bonded water. In order to examine the variation in more detail, principal component analysis was performed on the observation of spectra. Low means that the analyzed spectra were neither normalized nor different spectra. Three components were obtained again. The first component is the average spectrum. The second component is same as the component obtained for the pure water on the temperature change. The third component responsible for the spectral variation in the low wave number. The component resembles the third component found for salt solutions, although there is some difference between them. Loadings for apoptotic polar organic compounds resemble those for salts, suggesting that these loadings are independent of the element for considering the change of hydrogen bond network of water. 98.6% of the spectral variation can be explained by components 2 and 3. This is a score plot. So we stop here. And the mechanism of the variation in the urine-phase spectra of aqueous solution have become apparent to some extent. It is a future task to clarify what kind of the change of hydrogen bonding the obtained spectral components correspond to. This is illustration of the change in the molecular level, but I'm afraid that it's difficult to illustrate this point only by measuring this spectrum. So thank you.
Thank you very much, Professor Takayanagi. It was a very nice, interesting presentation. It's very nice to see we have been working in different groups and we get repeatedly the same results. Questions? We have time for one question only.
Thank you for your interesting talk. Could you show again one slide on which I would have a comment? The slide of the spectrum of Na2CO3 and NaClO4. Yes. It would be interesting. Just this one, yes. Maybe the after with the line exact. I'm just putting a question. No, yes, this one. Putting a question in the air, in the sense that I was hit by this graph because in the Hofmeister series we are aware of the fact that there are some ions that deplete one kind of water in the sense of the low density phase one and other that increase it. In quantum electrodynamics, the two phases are coherent phase and non-coherent phase. And if we are stuck to this vision, we should have just two components, no? And so the fact that we are changing their ratio should make that we should have that the isosbestic point of one plot should coincide also with the isosbestic point of the other one. Yeah. But this, as you can see, is not the case. Because you have the peak in correspondence of the isosbestic of the other. The peak of one plot is in correspondence of the isosbestic of the other one. So could be interesting because about this point, actually these two phases, thermodynamically speaking, are two, but dynamically speaking, maybe they are three, in the sense that the low density phases has a gradient that shades smoothly to the high density one, that in quantum electrodynamics correspond to the non-coherent part. And in quantum electrodynamics you can modelize the theory predict that ions are able only to get soluted in the water, not because they are solitary entities that are solvated by molecules, but because they create non-ideal, the bihucal plasmas that are located exactly in the intermediate phase. And this is interesting because certain kind of ions build up this part of water, that is the intermediate one, and other ones reduce it. So maybe this could be the answer on this hypothetical question about why the two isosbesting points are not coinciding, because we have three phases, no? And the ions is not only a binary system.
Yeah.
Thermodynamically speaking, it is, but not dynamically speaking. So I'm just commenting and putting this question in the air and see what do you think about it. Thank you.
Yeah, it's difficult, but I think there's at least three kind of phases and some equilibrium between them.
Yeah.
And
Yes, because there is one of the last slides. In fact, you show three.
yeah,
Very less or almost free hydrogen.
yeah,
This one. Exactly.
yes, two kind of hydrogen bonded water, but if the equilibrium between this one and this one and the abundance ratio of these two is constant, we can get some isolated point of different wave number. But I don't know why this constant abundance is achieved.
Maybe, this is my opinion, this is quantum electrodynamics framework can give a very consistent answer to this aspect. Maybe we could also discuss. I have some ideas. Thank you so much.
Thank you very much.
Okay, one more quick question.
Can you comment on the location of hydrogen bonding water 1 and hydrogen bonding water 2?
I have no idea now. Sorry.
Thank you very much. I recommend to continue this discussion in the break because we are really running out of time. So thanks again, Professor. Thank you very much.